So today's lesson is a brief one about two terms that were introduced last day with the PhET Waves on a String lab, and that is superposition and interference. So I want to start by demonstrating two of the last questions, just to make sure we're all on the same page for the kinds of observations we made. So I'm starting with the one that has you do pulse coming towards another pulse that is on the same side. So I'm going to let that one go down to a loose end because I'd already determined that a loose end pulse reflects on the same side. And I've paused it here just so we can do a little comparison of how high these pulses reach. I'm not going to use these so much as rulers as I am a straight edge for a reference point. So these two pulses are coming at each other, one from the left and one from the right. And if I let them step through, I'm not going to press play because I want to isolate a particular moment here. If I let them step by step reach that point where they are overlapping, I end up with a wave pulse where they've added together. And this is gets a term called constructive interference because those two waves are compounding each other. They're both on the same side and I'm getting a much bigger amplitude as a result. If I reset this, and instead of the free end, I switch it to a fixed end. This is the setting that lets me get a reflected pulse go back on the opposite side of the string. I'm going to get rid of the rulers because I'm not actually going to need them this time. I'm going to do the same thing. I'm going to start a pulse, and then I'm going to start a second pulse so that they head towards each other. And as I let these go step by step, I can find a moment as they are exactly overlapped where I get approximately no amplitude at all. Because I had some pulse of an amplitude of 0.76 centimeters on top and a pulse of the same amplitude underneath. So it would be like adding negative numbers in math. I have a positive 0.76 and a negative 0.76, and I result in 0. And then if I let them play again, the two pulses are traveling along their way. And as a result, I can get this on pretty much every cycle. The word that this one gets is destructive interference because I have some amplitude above and some amplitude below, and they cancel each other out. If I go back to my free end, the only difference is I'm going to get successive constructive interference on one side, destructive interference when they're on the opposite side, and then I can get another version of constructive interference underneath. So it doesn't matter that these ones are below the equilibrium line and that other one was above. The idea is just what happens to the amplitude. Is it bigger than it was on the individual waves, or is it smaller than it was on the individual waves? So one phenomenon we would normally investigate in class is how wave pulses behave when they meet a boundary between two different materials. So here I have on the left a thinner coil, which would be something like a slinky with a wave pulse traveling through it, and it is attached to a heavier spring. This would be something more like would be used to close a door or a gate. And what happens is my original pulse meets that end. Some is transmitted onwards and some is reflected back. And the key feature to notice in this is that the wave pulse that is reflected back in the original spring is underneath. If this coil here, the second one, is a denser material, this behaves like a fixed end. The pulse still travels through and it still does oscillate in that end, unlike with the wrench, but because it's heavier, it acts to reflect that pulse on the opposite side of the original slinky. The opposite would be true if I went the other way. If I went from a heavy material to a lighter material, you'll notice when it reaches that end, the light material does not act like a fixed end for that original coil, and the reflected part of the pulse travels back on the same side of the heavier coil. So we're looking today at a principle called superposition, which is the result of two or more waves passing through the same point at the same time. So just like how the simulation let us add individual pulses to demonstrate constructive and destructive interference, the same is going to apply to waves as a whole. And this is the principle of superposition, that I have two individual waves that, because they're passing through the same point at the same time, they're going to interfere with each other just like the pulses did. So if I take these two waves, the individual pulses were constructive when they amplified each other. The amplitudes were on the same side of the equilibrium line, and the result was that we had an amplitude that was twice as large. So we can do the same thing with waves as a whole. And if I were to imagine adding these two waves together, I would end up with something that has the same 0 points, the same equilibrium points, but the amplitude would be twice as large above and below. So this is what we call in phase. These waves are in phase because they're doing the same thing in their cycle at the same time. And the result is that much larger amplitude. I could also imagine a situation where instead of lining these two waves up in phase with each other, peak to peak, trough to trough, I could take the same one and line it up so that they are exactly out of phase, where the crest lines up with the trough and vice versa. And just like the others were out in phase with constructive interference, this is what we call completely out of phase. They are exactly a half a cycle apart. And if I add those two together, this would be just like the wave pulses on opposite sides of the slinky, where I would have 0 amplitude all the way along the wave. Now I can get degrees of this in between. If these were slightly off, I would have waves that are out of phase but not completely out of phase. And then I would get sections of constructive and destructive interference mixed together. And we'll look at an example of that in a minute. So while it's easy to see if waves are in phase or out of phase when they're directly lined up with each other, like if I put a second one of these down here, it's easy to see that these are in phase. They're at the same point in their cycle at the same time. And I can line up crests and troughs and so on. They don't necessarily have to be originating at that same point. If I were to take this same green wave and slide it over here, these two waves are still in phase because their peaks and troughs are at the same point at the same time. The difference here is that I'm offset sideways by a full wavelength. So this is something we call a path difference, where the waves are not originating from the same source maybe. The source is further to the right-hand side of my screen, but that these waves in the section where they overlap would still be constructive interference. And I could actually move this over again, and you can probably imagine where the next position is going to be where these waves will be in phase. If I bring this wave all the way over here, I have a second segment that is clear, and that makes up first 1 for the red section, and then 2 full wavelengths of this particular wave that this could be slid sideways. And you can imagine if I had this longer along my screen, I would have any number of wavelengths. As long as my path difference is an integer number of wavelengths, this will still be constructive in the parts where these waves overlap. And then there's a similar condition for what will happen when waves are out of phase, but maybe not directly lining up with each other. If I move this wave here, there's a small segment of a half a wavelength so that I end up at the opposite parts of my cycle. And then I can do the same thing. I can take my wave and slide it to the next position where I will be half a cycle out of phase to there. I have my original half wavelength here, and then I have another full wavelength to get to the next point in my cycle. So what I need here is an odd number of half wavelengths. I need to be 0.5 off, or 1.5, or 2.5 off. So to have that condition of destructive, my path difference, I'm going to call it n plus a half wavelengths. N is still an integer, but I don't want integer wavelengths. I want off by 0.5. The last thing I want to say about constructive and destructive interference is that it doesn't need to apply to the wave as a whole. Individual points can be constructive or destructive. So what I have here is two different waves that have been added together to get a very funny looking result. When I'm at a point in the wave that is constructive, for example, here, we have a situation where the first wave's amplitude is on the positive side, or above the equilibrium, and the second one is as well, and I end up with a wavelength, or sorry, with an amplitude that is bigger. So here I would have a point, I'm going to label this with a C for constructive. Similarly, if I look at a point over here where the wave 2 has an amplitude that is below that equilibrium line, and I extend my imaginary line downwards, this would be a point here that is destructive. The amplitude is not as big as the original wave number 1 here. So it doesn't have to be a wave as a whole is in phase and constructive or out of phase and destructive. I can create each individual point. So how this result image was created was by measuring those amplitudes above and below and adding those numbers. If it was above the line, treat it as a positive number. And if it was below the line, treat it as a negative number. And if I do that at just about every quarter cycle of this wave, so if I take this point and then the equilibrium and then this one down here and so on, and I sample my wave every quarter cycle, I can create this image. I could also go along and label more points. This one here is going to be constructive because it's larger than the original amplitudes. Something like here is going to be destructive. And I build up this picture of a rather complicated wave. And this is what most sounds are like. Most sounds are just not pure tones like those original waves we looked at in the first lesson, but are a mix of all kinds of different waves and different sounds adding together. Thanks for watching.